Welcome back to our course on memory device technology for AI/ML computing. I am your instructor, Dr. Shubhadeep from the Electrical Engineering at IIT Hyderabad. And today we will be beginning with a new module, which is Static Random Access Memory or SRAM. Till now in the course, we have looked at what is the basic compute architecture of modern day computing, which was nothing but the von Neumann architecture. We also saw what is the importance of memory hierarchy in implementing von Neumann architecture when the computational needs get very heavy or complex. We saw what was the rationale for the pyramidal memory hierarchy, how there are different elements in the pyramidal memory hierarchy. Furthermore, we looked at global trends in memory market, which involved innovations of each and every element in the memory hierarchy. And in the last sessions, we concluded the importance of memory array and also looked at the peripheral architecture as well. So with this background knowledge, I think we have enough context and enough introduction to go into a deep dive of individual memory elements. And that is what we will begin today with the SRAM cell. So just a quick recap of where in the memory hierarchy the SRAM cell lies. So do you want to take a moment and pause and think where in the memory hierarchy the SRAM cell lies? So if you have been following the course carefully, you will know that the SRAM cell lies at the top of the memory hierarchy, very closely coupled to the CPU. And it constitutes of the L1, L2 and L3 caches. This is a 6-transistor SRAM cell which I have represented over here. In this class, we will go into details of the structure of this SRAM cell. Again, in this structure that we saw, a more flattened out memory hierarchy, please take a moment to review which will be the parts which are covered by the SRAM cell. So I have indicated for your convenience the parts which are to be covered by the SRAM cell. This places in the entire memory hierarchy are covered by the SRAM cell. So important things to remember in context before we do a deep dive is that the place, as we just discussed, in memory hierarchy is closest to the core. So the focus whenever we build an SRAM cell or the peripherals around it is purely on performance. You would want to have SRAMs working with very high performance. So another synonym for high performance is having extremely low latency. If any information is requested from the codes, it should come from the SRAM or the L1, L2 or L3 cache in a very short duration. So the focus is always on performance. And since the focus is on performance, we have spoken about that there is a trade-off between latency, power consumption, and also latency and area. So you have to, of course, be a little bit more relaxed about few other considerations. Therefore, the density or memory density of SRAM cells, as we also saw in the previous class, is quite low. So you have low density, and as a result, you are only able to accommodate kilo to megabytes of L1, L2 and L3 cache. Also, we saw that these SRAM cells are quite expensive when implemented along with logic cells. Why is this the case? This is because they are consuming the same footprint, or they are accommodated in the same footprint as your logic transistors. In essence, as we will see, they are made from the same transistor technology which constitute your logic core. Finally, we have also need to worry about the power that these SRAM cells consume, and we will see that it is a significant portion of your entire logic chip's power. So if you want high performance, you have to relax some other considerations, and that is very important to keep in mind before we do a deep dive. Next, we will look at a very quick historical evolution of how SRAM cells have been integrated in computing systems. And a good way to look at is what was the position of cache uh, with time. So earlier, there were no concept of caches in the first place in the pre-1985 era. You had CPU, which was directly talking to your DRAM, which is your main memory. And then people realized that that is not a very good approach because there is a big bottleneck between the CPU and the DRAM or the main memory. This is where people realized that you need to have a cache memory which can store the most recent required data by the CPU. So, off-chip L1 cache was first introduced in 1985 to have some buffer between the main memory and CPU. But soon there was a big latency issue between the CPU and L1 cache. As a result, whenever we suffer from latency issues, we have been studying, important strategy is to have the memory on chip. If you have on chip memory and you don't have buses which are going out of the chip, you can really save on latency. And this was what was done. The level 1 cache was integrated in the same chip as the CPU processor. Once this was facilitated, there was a requirement for L2 cache which was outside the CPU, but still there was still a lot of latency between the L1 cache and L2 cache and L2 cache and main memory. So after a while, even the L2 cache was embedded within the CPU. But please understand that having on-chip memory is not without its own constraints. As you can see, the size of the CPU chip is becoming larger and larger, and therefore CPU chips will become more expensive because, as we have been discussing, in silicon CMOS technology, the footprint is what is directly correlated with the cost of the chip. In recent times, the recent architecture has different levels of cache, L1, L2 and L3 cache. And as we have discussed, because we have multi-core processing nowadays, with the CPU is not just one core, but multiple cores, L1 and L2 caches are given to each and every core, whereas L3 cache is common to all the cores. And this is something that we also saw in a floor plan CPU in the last class. Remember, in the last class, we saw an octa-core processor, and we saw that the size of the L3 cache was equivalent to all the 8 cores put together. So nowadays, as we will see, that SRAM cells are consuming a lot of area in the chip, not just the SRAM cells, but also the associated memory controller and memory peripherals. Right? So this is a very quick historical perspective, how the importance of SRAM cells has just grown. And when we were looking at the memory global market, there also we discussed a very important concept, that the size in terms of billion-dollar terms of standalone memory is almost equivalent to that of the on-chip SRAM memory. Okay, so that gives you the importance of how SRAMs have evolved. Okay, with this perspective, let's now go into core technical details. In this slide, we will introduce for the first time what is the structure of the SRAM cell. But before we do that, let's quickly recall these terms which are used in the SRAM cell. First is static random access memory. So what is static versus dynamic? Remember, both SRAM and DRAM cells which are used in caches and in the main memory are essentially volatile memory, right? So if you switch off the power supply, the information is gone. However, in SRAM cells or static random access memories, there is no requirement to do a continuous refresh. This is because, unlike dynamic random access memory, where information is stored on the storage node of a capacitor, here, as we will see, in SRAM cells, because of positive regenerative feedback, you are able to protect the data. Okay, so this is very important concept, and this is where the term static will come from. Next is random versus sequential access. Since we discussed that the core focus of SRAM or caches is towards performance, you need to have random access. We discussed that random access is the ability to read any bit line corresponding to a particular word line in any particular order, right? Therefore, random access is important for high performance systems versus sequential access where you can compromise on the latency, something like NAND flash or even magnetic tapes. Final thing that we want to discuss is this is essentially a memory element, not storage, because it is catering to the immediate needs of the CPU's computing data. Okay, so with this, let us look at the basic structure of the SRAM cell. So here we have indicated what is the basic structure of the SRAM cell. At the heart of the SRAM cell are essentially two cross-coupled inverters. So what is the meaning of cross-coupled inverters? As you know, inverters are devices which in digital CMOS logic invert the input. If the input is 0, it makes it 1, the output is 1, and vice versa. If input is 1, it goes to 0. And a simple symbolism that is used is this triangle. So you have inverter 1 and you have inverter 2. They are called cross-coupled because the input of inverter 2 is connected to the output of inverter 1, and that is through storage node 2, and the output of inverter 1 is connected to the input of inverter 2, and that node or that point or junction is called storage node 1. Important thing to realize over here, because this is a cross-coupled inverter, N1 and N2 cannot assume arbitrary values. N1 at all times has to be the complement of N2. If N1 is 0, N2 has to be 1. If N2 is 1, then N1 has to be 0. Okay, so this is a very important thing to consider. So at the heart are these cross-coupled inverters. Next is, it is not enough to store information in storage nodes N1 and N2, but it is important to also be able to access it. And this is where two transistors, which I have indicated here in green color, are placed. So these transistors are NMOS transistors, and they are connected. What is the job of these transistors? The job of these transistors is to give you access. It is to give you access to the internal storage nodes N1 and N2. And because they give you access, they are sometimes called access transistors or even pass gate transistors. Okay, so let us see what are the connections to the access transistor. As you can see, the source of the access transistor is connected of PG1 is connected to bit line, whereas source of PG2 is connected to bit line bar. What is the drain connected to? N1 and N2 respectively, right? So in essence, when this transistor is on, when pass gate 1 and pass gate 2, which are connected with each, the gates are connected to each other, when the gates are turned on or the transistor is turned on, the voltage on storage node 1 will be reflected on bit line, and the voltage on storage node 2 will be reflected in bit line bar. This also gives you an idea of the terminology. Why is these bit lines called bit line and bit line bar? This is because N1 is always the complement of N2, right? The last thing that we need to understand is how do you enable the gates of these transistors? As we had seen, even in the memory array architecture, the gates of access transistors is connected to the word line. By enabling the word line, what you are essentially saying is the outside world has access to the internal storage nodes N1 and N2 through bit line and bit line bar respectively. And we will see later how read and write operations are facilitated through this pass gate transistor. Okay. It is also worthwhile to see the complete 6T rendition of the SRAM cell. The complete 6T rendition of the SRAM cell is as follows. Here what we have essentially done is the inverter 1 has been expanded to one pull-up transistor and one pull-down transistor. From your basic courses in digital or analog CMOS, you may know that an inverter consists of a PMOS pull-up transistor and a NMOS pull-down transistor. They are called pull-up transistors and pull-down transistors because pull-up transistors pin the output to VDD, whereas pull-down transistor pins the output or tries to pull the transistor, the output to ground. Right? That's why they are called pull-up and pull-down transistors. Similarly, the corresponding transistors for inverter 2 are indicated in blue color. They are the pull-up 2 transistor and pull-down 2 transistor. Okay, and as you can see, the output of N1 is connected to the input of N2, and the output of N2 is connected to the input of N1. And this is where the terminology of cross-coupled inverter comes from. So I hope we have been able to capture or understand what is the basic structure of a 6T SRAM cell. Next, we will go ahead and talk about why is there a memory effect in SRAM cells. To understand why there is a memory effect in SRAM cells, we have to understand the concept of negative versus positive feedback. So what is this concept of negative versus positive feedback? In the previous slide, we saw that an SRAM cell is nothing but a cross-coupled inverters where the number of inverters is 2. What happens when the number of inverters is 3, or for that matter, any odd number? Okay, so what will happen is the same cross-coupled inverters, you can now say that this is inverter 1, 2 and 3. Why are they called cross-coupled? Because the input of the output of inverter 1 is connected to the input of inverter 2, and then inverter 2 input is connected to the output of inverter 2 is connected to the input of inverter 1, and with a feedback, the output of the last stage, which is inverter 3, is reconnected back to the input of the first stage, which is inverter 1. Right? So this is what is the structure. If you have done a course on digital logic, you will know that this is called a ring oscillator. Now, a ring oscillator is a very important structure in engineering of CMOS devices, and we will soon see why. Important thing in our context is to understand that a ring oscillator has negative feedback. What is the meaning of negative feedback? It simply means in this particular context that if I start with a value of 0 in the input of the first stage, the output will be 1, then the output of the second stage will flip to 0, then the output of the final or third stage will again flip to 1. So when this 1 is fed back into the input, this is trying to create a negative feedback. That means it is trying to de-strengthen the initial input. And it can be very easily shown that if there is a finite delay at each and every stage, which is more technically called the propagation delay of an inverter, there will be an astable ringing effect. What is the meaning of astable ringing effect? This structure will continuously flip from 0 to 1 at each and every node. And this ringing frequency can give us a lot of vital information. This ringing frequency, as you can see from this formula, can tell you what is the propagation delay at each and every stage. The formula is F, which is the ringing frequency, is equal to 1 by 2n tau delay or T delay. First, what is n? N is the number of inverters or number of stages. And as we discussed, to have a negative feedback, you will need to have n as odd number. It needs not be just 3, it can be 5, 7, anything. N needs to be an odd number. and the frequency of the ringing will give you what the propagation delay is. Therefore, ring oscillators are used heavily in logic systems to find what is the propagation delay of a particular technology node. Okay? At this juncture, it may be a very interesting question to ask. Can you think of a real life physical system which also behaves like this? A real life physical system which has a ringing effect, or it is astable. What is the meaning of astable? It is going from one position to the other position continuously without stopping. Simplest example you can think of is that of a pendulum. Pendulum is always going from one left corner to the right corner, and if you assume that it is a frictionless pendulum at its fulcrum, this will keep happening for eternity. So this is a good physical analogy or a physical system to imagine. Similar system that I want to deal with or want to discuss is a ball in a frictionless bowl. So this is a frictionless bowl. If I release a ball over here, because there is no friction, it will keep for eternity going from one state to the other state. In principle, there are two extrema states, but all the time the ball will go back and forth. This kind of oscillating system is also called a astable system, right? Because there is no particular stability point. Okay. If this was friction, if you had introduced some friction over here, then what would have happened? After a while, it would have come to the minimum potential energy point, which is the bottom of the ball. But in a frictionless system, this will be essentially astable. We are describing these analogy to physical systems because then it is a great way to imagine how to design our systems, and we will see that later on in our future lectures. Now, let's come back to the system of our consideration, which is the SRAM cell. In the SRAM cell, because the number of stages is even, the opposite effect is seen. Just imagine if inverter 1 output was connected to inverter 2 input and vice versa. This gives you a positive feedback. Why do you call it a positive feedback? Suppose I had written 0 at N1. So at the output of N2, after one propagation delay, at N2 I will get 1, and after the second propagation delay passing through inverter 1, I will again get a value of 0. So the value that I had forced or written at N1 is now getting positively enforced. This system is positively reinforcing the output in this system is positively reinforcing the input. And this is the fundamental reason for having the memory effect in a cross-coupled inverter, which is the heart of the SRAM cell. So this is a very important concept. Let me just repeat it for you. Since if I write any value N1 on N1, it may be 0 or 1, because it is connected in this cross-coupled inverter fashion with even number of inverters, always there will be a positive feedback. That means the output of the last stage will reinforce the output in the input of the first stage. This is exactly opposite of what was happening with the ring oscillator. And therefore, this system is called a bistable system. A bistable system. This is called a bistable system because there are two stable values. N1 can be 0, N2 can be 1, or N1 can be 1 and N2 can be 0. Okay. So what could be a good physical analogy to this kind of system? A good physical analogy to this kind of system is something that I want you to pause for a moment and closely think about it. So a good analogy to this kind of physical system will be a W-shaped potential barrier. As you can see, we have a W-shaped potential barrier and you have two stable states. Suppose I release a ball inside this W-shaped shaped potential barrier, the ball can be in two stable states. Either it can be in position 0 or it can be in position 1. Since it is or, not and, I have indicated this with dotted lines, right? Either the ball can be in this pocket or in this pocket. Just similar to our SRAM cell node N1 and N2. However, there is a finite barrier. Suppose now the ball is in N1 or the ball is in the first pocket. There is a finite barrier that I need to overcome to go to N2, right? Yes. So this kind of analogy of physical system will be very, very instrumental in analyzing and designing the SRAM cells. So as we saw, there are two stable states. In the case of SRAM cell, your storage node 1, 0, N2, 1 and vice versa, 1 and 0. Similarly, here also there are two stable states, or you can call it a bistable state. In addition, as we will see, there is also a metastable state. The metastable state in this case will be at the top of the barrier. Why is it called metastable? It is called metastable because slight push, a gentle push in either direction, and your ball will go and sit in one of the two stable states. So therefore, this place is called the metastable state. Okay. With this, we have introduced what is the basic structure of memory effect the basic structure of the SRAM cell. Why is there this memory effect? And in the following class, we will see in the actual SRAM cell, how is this memory effect manifested. However, I want to leave you here with an important question which will help you in clarifying the concept. And the question that I have for you, which we will discuss in the next class, is what would be a desirable height for this energy barrier? Would you want this height to be very high, or would you want the height of the energy barrier to be low? So please think about this question and we will meet in the next session.